Hello everybody, this is Dr. Bricker here with a review information for the final exam. So the final exam is Monday from 12:30 to 2:30, and it's online, similar setup to exam 3. So if I were to study for it, I would definitely watch this video, look back at the practice tests, and I'll remind you where those are in just a minute. Look at the exams that we've taken. So you should have a copy of the first one. I'm going to be posting a blank copy of the second one. Remember, we took the second exam right before spring break, so you didn't get a chance to get it back. But I will post a copy of the second exam too in the in this folder. And look back over the homework assignments. We've had quite a bit of homework, and then also take a look back through the notes. Now there is a bonus homework assignment that covers the entire semester, so you can take a look at that as well. Just another avenue. I'm not saying the bonus homework is the best way to study. I'm just saying it's just another way of another avenue that you could explore. But definitely watch the video, practice test, exams, homework, notes. Lots of material there. I think when you get to the final, you'll have seen almost all the problems in one form or another. And there are 20 to 22 questions, multiple choice and short answer. So really similar to exam 3. If you think about it, there's about 15 chapters or so that we've covered, and there's 20 to 22 questions, so usually there's 1 or 2 questions per chapter. So, very general. A very broad test, but not a very deep test. So it's just sort of the general information from the class. And just to refresh your memory, I'm in learning materials on Blackboard. Now, before we went to the online version, way down here, we had notes. So this is, everything up until spring break, labs, practice exams. So the first 2 practice exams are located in the practice exam folder. Now the practice exam for the third test is in the, I believe, week 14 or week 15 folder. Let's actually take a look. Yeah, I think it's in both of them actually. So that's where practice exam 3 is. So all the material on the final is from the entire semester. So, take a look back at those practice tests and also the actual tests. And I'll give you access to exam 2. You won't have your graded copy of it, but you will have a blank copy of it, just so you have a flavor of the type of questions that we had. Okay, so let's get started with the actual material for the final exam. Okay, so chapter 1 was kind of an intro chapter talking about like motion diagrams and significant figures. The real physics information started really in chapter 2, where we looked at different graphs of position versus time, velocity versus time, acceleration versus time, and what each of those graphs meant. This is where we first saw kinematics equations and free fall. So as far as graphs go, I'm talking about something like, here's time, here's position. What does this sort of graph tell you? If you have something like this, what does this tell you? Compared to what does this tell you? So this graph would give you, this is constant velocity. So if I were to take this and make it into a velocity versus time graph, I would have something like this. If I were to take this graph and make it into a velocity versus time graph, the slope of the tangent lines at each of these points keeps getting bigger and bigger, so this would actually be increasing velocity. Right? So that would be the velocity getting larger and larger. So velocity is positive, but getting bigger and bigger. This one, as far as an acceleration versus time graph, there is no acceleration because the velocity is not changing. So this would be 0. This one, if I were to do an acceleration versus time graph, this would be constant acceleration. So something like that. So take a look back through the information, concerning graphs and what we did with graphs. You'll definitely see a graphing type question. There's a good example on the practice test, the first practice test, and the first actual test. Then we had all the kinematics equations, velocity final, velocity initial, plus AT. Hopefully that rings a bell. This is, 16 weeks ago. velocity final squared, velocity initial squared, 2a delta x. And then the final one that we had, delta x initial velocity times time plus 1/2 at squared. So all these are good for constant acceleration. I'm sure you'll see some sort of kinematics problem on the test. So when you're solving these, you know what you're given, you know what you have to find. So you'll have to sort through and figure out which one you need. So the first one and the last one involve time, but they don't have, the first one doesn't have displacement in it, the third one does. The third equation doesn't have final velocity, but it does have delta x and t in it. So you've got to sort through based on what you're given and what you're looking for, which equation should you use. These are all for constant acceleration. Now the free fall one is, free fall, if you remember, just means under the influence of gravity. So it could be something going up, something going down, but just under the influence of gravity. So the acceleration in that case, I'll just put a little y there to remind you, negative 9.8 meters per second squared. Okay, so take a look at the kinematics equations, and also the end of chapter 2 we had a little bit with free fall. And remember, this free fall situation works with all of these kinematics equations. Okay, then we went into chapter 3. Up to this point in the semester, we were just describing motion. We weren't saying what was causing the motion. Well, I take it back. We're not quite yet to the point where we're going to say what is actually causing it. Chapter 3 is two-dimensional motion. Chapter 4 and 5 is where we start talking about what's actually causing it. So chapter 3, two-dimensional motion. The couple of situations that we talked about were projectile motion. So projectile motion. And then we also had motion on a ramp. So I'll detail both of those for us here. Okay, so for projectile motion, this is something moving in not only the x direction, but the y direction. So I'll make a little chart here, x direction, y direction. Now the acceleration in the x is 0. We're assuming there's no air resistance. The acceleration in the y, negative 9.8. The only equation that we have for the x direction is this. The x velocity is the displacement in the x direction divided by the time. That's all you have. It's kind of nice there's only one equation, but it's limiting because there's only one equation. Now in the y direction we have all the kinematics equations. There's the first one. I'm just really emphasizing that it's in the y direction. Here's the second one. Again, I'm really emphasizing that it's in the y direction. Initial velocity y squared plus 2a displacement in the y. And then finally, displacement in the y, initial velocity in the y times time plus 1/2 acceleration in the y, t squared. Now, we know what the acceleration in the y is. It's this number. And then you can use whatever appropriate kinematics equation that you have. The other one I would just add here is the range equation. It could be helpful in certain situations. Sine of 2 theta divided by g. I'll just put g there. It's the g of whatever planet you're talking about. So we did some problems on the moon, some problems on the Earth. So the range equation is only good for this situation. You leave at one level, you get back to the other level. And the range equation gives you the x displacement. So here's theta. This is the overall velocity in the equation here. So we saw that the maximum range occurred at 45 degrees, because then you'd have the sine of 2 times 45, or the sine of 90. That's as big as the sine function can be. We use the idea that at the highest point here, the y velocity at the highest point is 0. So look back at the first test. This was included on the first test, this projectile motion, two-dimensional motion stuff. Okay, good. So you have the resources to look at, really, the test, practice test, homework. So take a look back at those. Motion on a ramp. I'll just draw the picture here. You don't have to redraw it every time. as far as the final exam goes, it's online, so you have access to a lot of resources. But I think I would still build a formula sheet just so you have all the information at your fingertips. You have 20 to 22 questions, 2 hours to do it. So on average, maybe 6 minutes per problem or less. But if you have to look through your book, try to figure out, what's going on, it could take a while. So I definitely would have some sort of little study guide built for yourself. So if this is theta, this is a mass on a ramp. Here's the free body diagram. Normal force, the weight is straight down, mg. We can break this into components. This is how we looked at motion on an incline. So if that's theta, this is theta. This part over here is mg sine theta. This part over here is mg cosine theta. Now in terms of the acceleration, I'm assuming that there's no friction. The acceleration down the incline this way, and again, just to refresh your memory, x and y. The acceleration in the x was g sine theta. And then you can still use all the kinematics equations that we had. Okay, so really from chapter 3 we started to do two-dimensional motion, projectile motion, or motion on a ramp. Okay, so I'm sure you'll see one or the other of those problems. Okay. Chapter 4 is when we first started talking about forces. So chapter 4 and chapter 5 are really related to each other. There's Newton's 3 laws. Now the first law will just help you solve problems. An object in motion stays in motion. The second law is the one that you actually have a formula for. F is equal to ma. And this probably brings back memories to you. And then you have to fill in whatever goes in the blank there. So free body diagrams help you to put in the part that goes here. What are the actual forces? The third law is for every action there's an equal and opposite reaction. And the same thing, that can help you solve some different problems. So we did a whole bunch of homework questions on Newton's second law, both from chapter, so this is again chapter 4, chapter 5. So take a look back at those. The other thing I'll remind you of are the specific formulas for friction. So we looked at a lot of different forces, normal forces, weight, also friction. So kinetic friction is the normal force times mu sub k. Static friction is less than or equal to the normal force times mu sub s. So the maximum amount of static friction is the normal force times mu sub s. So static friction is the frictional force that is only as large as it needs to be. So this could be 0 if you're not applying a force. You start applying a force, then static friction is there. So imagine you're trying to push a box or something. You try to push it, it doesn't move. Okay, so before you pushed it, there was no static friction. And then when you start to push it, now static friction gets larger and larger and larger until you overcome the maximum amount of static friction, and then we have kinetic friction. So take a look back about this idea, both on the practice test number 2 and the actual test number 2. Okay, so if you remember the way we did those, figure out if you overcome the maximum amount of static friction, and if you have not, then static friction is just equal to the applied force. Now if you have overcome static friction, then you're in the kinetic friction regime, and you can figure out how much that is. Okay. After chapter 4 and 5, we went to chapter 9. So there's 2 kinds of problems from chapter 9, and I'm sure you'll see one of each. The first is there's an outside force. I'll start from the beginning here. It's the impulse type problems. Impulse, force times time. That gave you the change in momentum. So final momentum minus initial momentum. Momentum is mass times velocity. Here's a final way of writing it that I could think of. So impulse units, newtons times seconds, which is equal to a kilogram meter per second. So these are the kind of problems where maybe you have force, time, mass, velocity. You're probably given 3 out of the 4, and then you've got to solve for the 4th one. Just to be clear, you have to take into account direction. That's what this is reminding you to do. Remember the little vector sign. If right is positive, left is negative. So we did problems like a ball coming in, bouncing off a wall, going the other direction. So if a ball is headed this way at, say, 20 meters per second, hits a wall, bounces back here at maybe 10 meters per second, you have to know that this is negative because you're going in the opposite direction. So if you said this was positive, that's negative. So you have to keep track of that in terms of momentum. It's a vector quantity. So I'm sure you'll see one of these. Hopefully this rings a bell. This is again from the stuff that was on the second test. So look back at the homeworks that go along with that. Chapter 9 homework assignments. So you'll see something like that. And then the other kind of problem from Chapter 9 were collisions. So Chapter 9 is a large chapter. So I'm sure you'll see one of these type of problems, and then you also see a collision problem. So whenever there's a collision, the way that you solve these is the initial momentum is equal to the final momentum. We talked about maybe two general classes. The perfectly inelastic collision. So what this means is sticks together. So take a look back at those. And then we just had generic inelastic collisions. I'm not going to put a completely elastic collision on the test. Completely elastic is also the initial kinetic energy is equal to the final kinetic energy. Remember, in general, this is not true. There's no kinetic energy theorem. So don't use this to try to solve collision problems. Unless they specifically told you it was completely elastic, this doesn't work. There's no such thing as this, other than the special case of elastic collisions. So just be careful when you do these. The initial momentum of the system is equal to the final momentum. There is no outside force. If this is 0, there's no change in momentum. That means the initial and final must be the same. So take a look back at the sticks together kind, and then just the generic, regular old collisions. Not the not stick together ones, I guess I'll call it. Not stick together. Now on the second practice test and the second actual test, we had both types. Okay, but I'll probably pick one or the other for the final. Okay, Chapter 10 is where we first started looking at energy. So we went from 9 up to Chapter 10, all about energy. A few different kinds. We had kinetic energy, 1/2 mv squared, gravitational potential energy, mgy, and spring potential energy, 1/2 kx squared. Here I use ke for kinetic energy. There's another k floating around here. This is lowercase k. This is the spring constant, so you have to be careful. So we did conservation of energy. We looked at the energy before something happened, the energy after something happened. We did like roller coaster problems, if you remember. You start up here. So you start up here with a certain amount of energy. I'll just call this energy 1. And then down here, energy 2. This is maybe all gravitational potential. This is some gravitational potential plus some kinetic energy. It's very complicated, the motion. You come here, angle keeps changing, you're going really fast, then you slow down. This is actually part of circular motion. So if you tried to analyze this from beginning to end, you could do it. It would just be hard. But with conservation of energy, the initial is equal to the final. So you'll see some kind of, using conservation of energy problem on the test. I'm not saying it's going to be gravitational to kinetic. I mean, we also had on the second practice test, second actual test, where we turned like kinetic energy into spring potential energy, something we called the Aldi's problem at the time. So if you have a runaway cart with kinetic energy, it hits a spring. That kinetic energy turned into spring potential energy. So we did a lot with this energy conservation idea. So take a look back at that. You'll see one of those sort of problems. The other big thing from Chapter 10 was the work energy theorem. So work is F d cosine theta, and that actually gives you something. It gives you the change in kinetic energy. So it's the final kinetic energy minus the initial kinetic energy. So 1/2 mv final squared minus 1/2 mv initial squared. So what you could use this for is problems with mass, velocity, force, and distance. So the impulse relationship, mass, velocity, force, and time. Here it's mass, velocity, force, and distance. So the unit of energy is joules. Regardless of what type of energy you have, the unit is joules. A Newton times a meter. What is this theta here? So if you have a force, I'll just call this maybe tension, and you have a normal force, mg this way, that's the angle. So this is the part of the tension that actually gets this thing to speed up, right? So F cosine theta gives you the part of the force that is lined up with the way you're moving. So if this thing is moving this way and Tx is this way, the work is actually positive. Now if there were friction back the other way, this thing would be slowing down. The work by friction would be negative. Okay, so lots of information in Chapter 10. Go back through the notes and look at the homework, practice tests again, actual tests to refresh your memory on this. You'll see some kind of work problem, maybe with the work energy theorem. Now, these problems, this work energy theorem and the impulse relationship, you could usually do that with kinematics, but you'd have to use kinematics in conjunction with Newton's second law. You could use kinematics equations to solve these problems if you knew what the acceleration was, and maybe you can get the acceleration from Newton's second law. Okay, let's look at the next subject that we covered. Okay, so this remaining part really is from the third test. We looked at circular motion, so we went back to Chapter 6, and I'll just put in parentheses here 3 because we looked at the a little bit when we did Chapter 3 originally. We didn't cover circular motion. I saved that little part for when we did Chapter 6. So circular motion. The part from Chapter 3 though is this: whenever you go in a circle, there's an acceleration towards the center. Towards center. So uniform circular motion, constant speed. Here's the magnitude of the acceleration. This comes from Chapter 3 actually. The Chapter 6 part is like this. The net force is ma. This is Chapter 4 and 5. It's just when you're going in a circle, it's a special kind of acceleration called radial acceleration towards the center. And then we have mv squared over r. I could plug that in for the radial acceleration. And then this part is the same. What are the forces towards the center? So we did a lot of problems, masses on strings going in a circle. The practice test was a situation like this. It's a car going over, through a circular part here. This is the radius, something like that. So we've got normal force this way, mg towards the center. Sorry, not the best vector drawing here. Towards the center is mg. Now I drew mg bigger than normal force because there has to be a net force towards the center. So as far as what I put in here, I know there has to be a net force towards the center whenever you're going in a circle. So then I can put, mg minus the normal force. And then I can solve for the normal force. The actual test, we were going through a dip in the road. We did things like masses on strings. So this is an overhead view of a mass. So you're looking down on the picture. This is some distance r. So always has to be a force towards the center. This could be tension towards the center. And again, this is an overhead view. Maybe this is going in a circle like that. So same thing, you would do net force, ma, special kind of a, because you're going in a circle, mv squared over r. Then what's the actual force towards the center? In this example, it's the tension. And you can solve for the tension that way. So you'll see something like, there's going to be some centripetal force type problem. On your whatever sheet you're making to study with, just know that this is the procedure. Net force, MA, special kind of A. What is the force towards the center? Now this example, there only is one force towards the center. In this example, there was a force towards the center and a force away from the center. So that's why I had to take that into account. So take a look back at all those examples that you saw from the homework and things like that. The only other thing to add from this chapter, I think, is that the speed is 2 pi r, the distance around a circle, divided by the amount of time it takes to go around a circle. So sometimes you can use this also to solve problems. Or if you want to, you could write it as 2 pi r, and then 1 over the period is the frequency. So be careful, this is tension. This is period. So also in chapter 6 we had satellite motion. So I won't put a satellite motion problem on the final exam. Okay, so your limit, look back at just, solving these ones where you have something towards the center. Okay, then we got into chapter 7, and chapter 7 was rotational motion. So this is circular motion, things actually going in a circle. Rotational motion are things rotating on their own axis. And to get something to rotate along its own axis, you have to have a net torque. So we looked at some torque problems. So torque is R perpendicular times F, or F perpendicular times R, or RF, sine of the angle between R and F. So like for example, if you had, I'll just do like a shape like this. If this is the force, here's the pivot point, this is R, you could figure out the torque. In this case, they're actually perpendicular to each other. That's maybe the easiest case to visualize. Another one though would be this. This is still R, but what if you had F at like this angle? Well, torque depends on the perpendicular part of the force. So here's F perpendicular. Okay, so the torque here, same thing, it's R, F perpendicular. So you'd have to figure out how much of this force is perpendicular to the lever arm. Okay? So, let's refresh your memory on torque. That's what gets things to rotate, torque. So if it has a solid shape, like maybe it's a pulley or something, we looked at some pulley problems. Let me go to the next piece of paper. This will probably refresh your memory because we didn't do it too long ago. If you have, say, 10 newtons this way and 5 newtons this way, and this is out to the radius, same side over here, you could figure out the net torque, right? This would be the net torque. This would be the torque because of the 10 Newton force, which would be 10 newtons, and the distance to where it's applied. So rotational world is just one more step. It deals with force, but where's the force applied? And then minus 5 newtons, and the same thing, R. You can figure out the net torque in this situation. So what does the net torque give you? It's the moment of inertia times angular acceleration. So the net torque is I alpha, and then I guess really what I would have done is put this part in the box here. So this is the rotational version of Newton's second law. Net torque, I times alpha. The net torque, I'll just write it to make it really explicit. 10 newtons times R minus 5 newtons, because that makes it rotate the other direction, times R. Okay, so this is angular acceleration. And this is moment of inertia. Inertia. Okay, good. So again, the rotational world is just a little more complicated. Moment of inertia depends on the mass, but what shape do you have? What's the size of it? So you always have to take that into consideration. I will give you like the formula for moment of inertia if we need to. If you think back to the third test and the third practice test, I think we had like a solid cylinder where the moment of inertia was 1/2 mr squared, but really it depends on the shape. Okay, so you'll definitely see some version of torque or Newton's second law. So, go again, I keep saying this, but go back over the third practice test, third test, and the homeworks that went along with that. The other thing I would say from this chapter is V is equal to omega times R. If you remember from the test, this is translational velocity. This is angular velocity. They're related to each other. Angular velocity, like this is, I think it was Ahmed and Jacques going on a merry-go-round. The farther you are, I think Ahmed was over here, Jacques was over here. Now if you're on this merry-go-round going in a circle, Ahmed and Jacques have the same angular velocity because they're going through the same angles in the same time. But the translational velocity of Ahmed is greater than the translational velocity of Jacques because Ahmed goes through a greater distance in the same amount of time. Here they're going through the same angles in the same amount of time. Okay? Chapter 8 then, the part of Chapter 8 we only did the first 3 sections of Chapter 8, balancing forces and torques. So sometimes when we did Chapter 4 and 5, you could just use forces to solve equilibrium problems. In Chapter 7, you could use just torques to solve some problems. But sometimes you need both ideas to solve problems. Before I forget, though, I did not put rotational kinematics equations on the test. So there's nothing like omega final squared is omega initial squared plus 2 alpha delta theta, anything like that. It's more of an overview, something like what you've seen on the third practice test. Okay, so then again from Chapter 8. Okay, so we use both of these to balance out, to solve some problems. So as far as problems go, it's something like, this. This is from the third test. So here's an arm. Here's the weight straight down. Here is the force of the bicep up. There's a small lever arm over to the bicep muscle, a larger lever arm over to the weight. So if you're going to balance the torque, so the torque from the bicep muscle is equal to the torque from the weight, because it's not going anywhere. If this is a big lever arm, and this is a small lever arm, this force has to be big, because you're taking a big force, small lever arm, smaller force, bigger lever arm, but you can get those to actually balance. So you'll see some sort of a balancing torques problem on the test. Okay, so look back at those. We had things like signs hanging. We did this kind of a problem. So we have tension here. There was some kind of sign hanging from this beam, and you want to try to figure out like the tension in this rod. So we did this problem. Here's the weight of the rod itself. Here's the weight of the sign this way. Tx that way. You want to figure out the tension. You'd have to use torques to actually do this. So just to give you an idea of the kind of problems that come from Chapter 8. Balancing torques this way, balancing torques this way. So again, take a look back at the homeworks and practice tests. Okay, then we went on to Chapter 14, and again, we didn't cover all of Chapter 8. We didn't cover all of Chapter 14. From Chapter 14, which is simple harmonic motion, we did masses on springs. So when you have a mass on a spring, the period is 2 pi square root of m over k, or the frequency is the inverse of that, so this would be 1 over 2 pi k over m, because the period and the frequency are inverses of each other. So when you have a mass on a spring, as long as you know the mass and the spring constant, you can get the period. The amplitude doesn't come into play at all. So a mass on a spring might look something like this. This is its relaxed length, and we did the lab on this also. And you stretch it out to here. This is called the amplitude, and you let it go. This is where the speed is 0, and the acceleration, the magnitude of the acceleration, is a maximum. Here the kinetic energy is 0, but the spring potential energy is as big as it's going to be, 1/2 Ka squared. So you let it go. It passes through equilibrium, So here at equilibrium, this is where the kinetic energy is a max. That means the velocity's got to be a max. And the spring potential energy is actually 0 because it's not stretched or compressed anymore. And then the spring comes back here. This is the other amplitude where it's compressed. This is also this direction. And everything that applies over here applies over here. So I don't have to rewrite it again. Kinetic energy is 0 because it has to stop for an instant. The acceleration is a maximum. All the energy is spring potential. And then in between A and 0, here the energy is made up of both spring potential and kinetic energy. Okay, so I'm sure you'll see something dealing with the period. Also, if you think back, what's going on at equilibrium? Is it where the speeds of, where's the speed of maximum? I'm sure you'll see maybe one question like that, or at least you can use that information to solve a question. Okay, so look back at simple harmonic motion. This is the most recent stuff that you've seen, so hopefully it's a little fresher in your memories. This still works, by the way. Spring potential energy is 1/2 kx squared, so sometimes that will help you solve problems as well. Okay, spring constant. Chapter 15-16, that's where we looked at standing waves. So we just did the first 2 sections of 15, and then we did waves on a string. So chapter 15, 16. The big takeaways from 15 and 16 is the wave speed. It's the frequency times the wavelength. It's also the square root of tension divided by the mass per length. Frequency, wavelength, this is the tension, and this is the mass per length, so kilograms per meter. So be careful, it's got to be in kilograms per meter. Now if you have a standing wave, the wavelength is 2L divided by the mode. So M here means mode. L is the actual length of the string. So standing waves look like this. I'll just give you an example. 1, 2, 3, 1, 2, 3. So here's a wave on a string. This mode would be 3. So if you knew the length of the string, you could figure out the wavelength. The wavelength is not the length of the string. The wavelength is 2L over the mode, the amount of antinodes. So 1, 2, 3 antinodes. You can get the wavelength from this formula. Okay, so if I wanted to, I could take this for wave speed and combine it with this formula. So let me do that. So frequency times the wavelength, but now the wavelength is 2L over M. So I've just plugged that in for the wavelength. That's equal to the tension in the string divided by the mass per length. If you want to, I can just take this another step. I can square this whole thing. So then I would have 4 frequency squared, length squared, mode squared is equal to the tension divided by the mass per length. And then you could use that to solve problems. I mean, this is a perfectly good formula. They all are. Here's just, with the square root gone. And this is mode 3, the fundamental frequency. Fundamental, that's where the mode is equal to 1. So, if it's the fundamental frequency, if you just plugged a 1 in here, that would go away. So what does the fundamental frequency look like? Well, it's this one. So here's the length. Okay, same thing. This is not the wavelength again. The wavelength would be 2L over M. So the wavelength in this picture, if this were the length, it's actually, and mode is 1, twice this, right? This is like half of a wavelength that you see there. Okay, so you definitely see some kind of standing wave problem on the test. So this is all the standing wave information right here for you. Okay. Next thing we did, we went back and looked at fluids. So fluid statics and fluid dynamics. You probably have seen this since about 4th grade or something. Density, mass divided by volume. This is a kilogram per cubic meter. So the fluid statics part, we looked at pressure at depth. So if you know the pressure up here, you could figure out the pressure at whatever depth you're talking about. And this is the pressure down here. So the pressure down there is the pressure at the top plus rho g y. And you can figure out the pressure here. Okay, so this is the absolute pressure. This is, you're taking into account whatever you have here plus this. So this is absolute pressure. The gauge pressure is just this. It already compensates for atmospheric pressure. So if you have a tire gauge, your tire gauge does not measure absolute pressure. It doesn't add the atmospheric pressure to whatever pressure you have in your actual tire. So this is just the gauge pressure, this part. Pressure gauge. And then this would be the absolute pressure. Absolute. The pressure up here, usually we use this for atmospheric pressure, times 1.01 times 10 to the 5th pascals, and a pascal is a Newton per square meter. Okay, so that's the pressure at depth. The deeper you go into a fluid, the bigger the pressure would be. It doesn't matter how wide it is, it matters how deep it is. Okay, also fluid statics, we looked at the buoyant force. So buoyant force is the density of the fluid, volume of the fluid that's displaced, times g. So this is kind of a new force that we had. You can still use it with the chapter 4 and 5 stuff. So on the practice test, actual test for exam 3, we had this problem, if you remember. And we wanted to figure out the tension in the string. So here's tension. There's also a buoyant force that's up. And then we've got the weight that is down. So you can imagine if you submerged something in a fluid, the tension in the string is going to be less. So in this problem, that we'd have tension up plus the buoyant force up is equal to the weight. And I'm just giving you an example of a possible problem. I'm not saying that this problem is going to be on the test. And then you can figure out the buoyant force. Weight minus tension. So same thing, weight is mg. Oh, actually, I think on the actual test, we figured out what the tension would be. Weight minus the buoyant force. Now, if there is no buoyant force, the tension is equal to the weight. When you have a buoyant force, the tension is less. And you have to take that into account. So we had this problem. One fun problem from the homework assignment that went along with this was, if you remember, we had a hippo standing at the bottom of a river, and they can easily walk around there because there's the buoyant force is supporting them, and they can move around a lot easier than they can on ground for that reason, because they're really massive. Okay, so really the fluid static part, it would be something like one of these. Pressure at depth or buoyant force type problems. So make sure that you remember how to do those. And then the fluid dynamics part, we had fluid flowing. We just looked at laminar flow, nothing with viscosity or anything like that. So the volume flow rate, the amount, cubic meters per second, this is equal to the area times the velocity. Now be careful. Usually it's a pipe like this, right? So if this is the area and it's a circle, the area is pi r squared, or it could be pi d squared over 4 if you want to look at the diameter. Okay, so that's the radius. This one's the diameter. Okay, so volume flow rate, area times velocity. Now it could be a case where the pipe gets narrower. So this could be like radius 1, diameter 1, area 1. Over here there would be radius 2, diameter 2, velocity 2. So whatever volume goes in here, it's the same as the volume. I couldn't see that, sorry about that. velocity 2, radius 2, diameter 2. So if water's flowing through here this direction, or whatever fluid it would be, it's going to speed up when it gets narrower. So then you'd have area 1, velocity 1 is area 2, velocity 2. Or if you want to write it in terms of the radius, velocity 1, radius 1 squared, right, because it's pi r squared. Velocity 2, radius 2 squared. Or finally, getting a little carried away. Velocity 1, diameter 1 squared is equal to velocity 2, diameter 2 squared. Okay, so you'll see some sort of fluid flow problem. Just to give you a heads up, I won't put a Bernoulli's equation problem on it. I'll leave it something like this. You go from one diameter to the next. Or it could just be one, calculate the volume flow rate for a given situation. Okay, and that's the last thing that we did. Again, I kind of pointed out what you could study. There's that bonus homework, which might be helpful. Also, I mean, I think I would go over, watch this video, look over the test, the homework, and then if you have time, do the bonus homework. That's the way I would approach it. All right, if you have any questions, let me know. You have a whole week to go. This is really the last thing for us to do during the semester. So, don't hesitate, please, to email me. We can set up a virtual meeting and kind of go from there. All right, 1 week to go. Hopefully everything's going well with you, and I'll talk to you soon.